Okay, today's video is going to talk about when we can use this Laplace, and it's a confusing topic. I apologize ahead of time, but so basically we're going to cover what is called exponential order, and that's going to tell us when we're going to be able to use the Laplace for our purposes. All right, we left off with the first video on this topic, which was the definition of the Laplace, which is an integral, and it transforms us into a new domain, okay, where we could resolve our it's an f of s domain, where we can resolve our function, our differential equation, and then then when we get a solution in this exponential domain over here, we could bring this back into the f of t domain and have a solution to the differential equation. Okay, we then concluded with the Laplace of 1, okay, which gave us a solution of 1 over s. And so here I'm going to just pick up on that and explain how if we have the sum of functions, we can do this. We could say, provided both integrals converge, okay, we can take the Laplace of the sum of these two functions, and then it would be the same as the Laplace of each individual function, okay? And this is by virtue of the definition of the Laplace, this here, okay? And so if you notice, where alpha and beta are constants, we're pulling those out front of the Laplace-ing operation, okay? So without effect. So you could argue or say that, well, what if I had the Laplace of a constant of 3 instead of 1? Well, then you can pull the 3 out front of the Laplace, and then you would do the Laplace of 1, which would give you 1 over s, and then finally multiply the final solution of that in the f of s domain by the constant of 3. So you would get 3 times 1 over s with 3 over s. Okay, and that works for these. Because the Laplace is a linear operation, we can take care of this in this manner and break it up and do the Laplace of each of these individually and get an f of s for each one of these. And then, of course, the constant is just acting as a constant. As we mentioned, that's also part of the linear operation things that are allowed. Okay, so now so we're going to say here that the integral which defines the Laplace transform does not have to converge, although for what we're doing here, we're going to find out we have to have it converge, because if it converges, then it exists. Okay, we have the existence of a solution. All right, so for instance, here's two examples that do not exist. One is the Laplace over 1 over t, nor the Laplace of e raised to the t power raised to the second power. Okay, this function does not, these do not exist, meaning they don't converge to us. Okay, so although we state so now we're going to state sufficient conditions which guarantee the existence of our Laplace. Okay, all right, so we say let f of t be piecewise continuous for values of t greater than or equal to 0. Now you say, well, what's piecewise continuous? Well, meaning it's continuous on intervals between a finite number of discontinuities within the limits of the integral a to b. Okay, so you could have a hole or a hole here and a hole there, what have you, but in between it is continuous. So therefore, as long as it's piecewise continuous and it has a finite number of these not an infinite number of discontinuities, a finite number that can be taken care of, then we can operate the Laplace is fine to use in here. Now, here we go, a little more conditions. If the absolute value of the function f of t that you're Laplacing, this is the function you're Laplacing, is less than or equal to m times e to the ct, where c is a constant, m is constant as well, for t greater than some large t, okay, and for t greater than 0, then the Laplace f of t exists for s greater than c. So let's see what this is saying in a graphical manner. All right, so visually understand this, we discuss exponential order. Okay, so if f is an increasing function, okay, this is in something that you've heard about. Well, is the function increasing? Okay, means every point after the point before it is increasing. Okay, so if f is an increasing function, okay, and if we took the absolute value, it could mean a decreasing function as well. Okay, a decreasing function, or right, one or the other. But then the absolute value of f of t must be less than m e to the ct, where t is greater than some large t. So this means, and then the interval is large t to infinity. Okay, so watch. Here's this m e to the ct. It's raising up, as you know, this function would look something like this. Well, here's your f of t, assuming that this is some f of t out there that we're examining, or we're doing the Laplace on. Well, as long as at some t, this f of t lies below the m e to the ct. And if you're below it, then you're okay. And that means this function f of t is of exponential order. Okay, and that f does not grow faster than m e to the ct, where c is a positive constant, past this t point, you see. Before it doesn't matter, it could be above it, what have you in the beginning, but at some point then it lays down, but it has to be increasing or decreasing function again. So functions with this exponential function as an upper bound, with this m e to the ct as an upper bound, t greater than large t, are said to be of exponential order. All right, so here's some examples of ones that this applies to. So say f of t is just t, so it goes up 1 to 1, but that's under e to the t all the time. So therefore, everything's fine here. This works. Okay, it exists. Okay, guarantees our existence here. Here you have e to the minus t. Well, that's in the absolute value. You put that in there. It's less than e to the t. See, so here it is. You see, so minus t is what you recall from pre-calculus. This is this function here is decay, right? This is exponential, right? This is growth. So you're underneath, the decay is underneath the growth, so you're okay. So even at t is 0, and here t is equal to or greater than 0. So because that's what it says, it has to be less than or equal to. So we're equal to it here at 0, but it's allowed. So your large t starts here. Your large t starts at 0 here as well. Okay, take a look at this one. This is f of t is 2 cosine t. Okay, so absolute value of that is less than 2 e to the t, and you're fine. Everything's good. But now go back to the one that I said was not going to work. E to the t squared is not of exponential order. So you're going to see that here's your e to the ct, and here's your e to the t squared. Well, it works up until some point, and then all of a sudden it shoots up faster than e to the ct, and therefore it's not going to work for our purposes in differential equations class. All right, so any n, this is just telling you that for any n that's a positive integer, okay, t to the n, is always going to fall less than this, so it's going to be okay to use it. And you can do you can divide these two. You can divide this, and then you get this has to be less than m for t greater than large T. And someone was able to prove this. Remember, you're proving that this limit exists by taking repeated applications of L'Hopital's rule, and it shows this is true. Okay, so where t to the n, where n is 1, 2, 3 to infinity, right? Okay, so this works. Okay, so notwithstanding that these conditions are sufficient for our use, but not necessary for the existence of Laplace transform. Okay, so let me just read something here, and this will suffice what we're saying. So throughout our work, and or at least this chapter of Laplace, we're going to only be concerned with functions that are both piecewise continuous and of exponential order. We note, however, that these conditions are sufficient but not necessary for the existence of the Laplace transform. Okay, so in other words, the Laplace transform can handle things that don't exist, but then it wouldn't be value to us. So we're going to stick to this piecewise continuous and exponential order of functions, and for our purposes. So that's the difficult chapter, and we'll go back into actual examples of Laplacing different things as we move forward. Okay, thank you.